So you should consider my talk as a background for the previous talk. Maybe the correct order would have been different, but still. So I'll talk about limits of differentials. And differentials could be holomorphic, meromorphic, or what I'll call real normalized. I have a strong feeling, even though this is what my interest was originally at, I'll probably won't get there much. And when I say limits, this will be on nodal, on stable curves, on nodal Riemann surfaces. So let me say what kind of goals could, yeah? Thank you, Kurt. Please do so again when needed. Goals. 1, what kind of objects occur as limits? So this kind of was implicitly present in Adrian's talk. I'll spell it out very carefully, and I'll try to explain to you that somehow if you're an algebraic geometer, you know the answer from the start. You don't know the answer to some other questions from the start. Second question could be describe all possible limits. So the first question is to say, basically, if I have a degenerating family in a suitable sense, what kind of an object should I consider on the limit curve as a limit of differentials? And the second question is to describe all possible limits that can occur. And I will only talk about this two. What Adrian talked about was goal number 3, which is compute the class of the closure of a stratum of abelian differentials. Well, for me, meromorphic differentials would be perfectly as interesting because they have to occur anyway. And this is what Adrian talked about. This sort of implicitly or explicitly, depending on your luck and circumstances, will use the answer to 1 and 2, which was somehow swept under the cover, and I will now pull back the cover and show you the ugly stuff that's there. Maybe not so ugly. If you want to be very optimistic, you may have further goals. You may want to construct a nice compactification. I don't want to spell out what nice means because I'm not going to go there. But somehow if you take a closure, it's some moduli space of something, and you would like to be able to explain that the boundary objects are blah, which we do, but then you want to say they fit in nice families. If you're a good algebraic geometer, you would want to find moduli space of something. I'm not sure that anybody has claimed they know how to do that. And number 5, which is far out, so this is was Adrien Sauvage, Dmitry Zvonkin, as we just learned. Number 5 would be to use all of this for orbit closures, etc. And I'm afraid this is the only place in my talk where you will see the SL2R. This is the entire dynamical content you will have. But hopefully, you may already be convinced, and if not, I'm happy to convince you privately, but not in public, that this may be useful. So the goal is to try to compactify. And as you know, if you study your favorite Teichmüller curve, it degenerates somewhere. And it may be useful information for you to know where it degenerates. If you're interested in higher dimensional orbit closure, it may be even more interesting because maybe the locus where intersects the boundary is bigger and you would be able possibly to extract more information from it. I mean, I'm not doing this now, okay? I would be happy to do it also. Okay, so this is the goals. I'll only talk about this, but this is somehow where I think this fits in the general scheme of why people might care. I might care for other reasons, but never mind that. Okay? Now let me make the next disclaimer. I would love to say theorem, put a dash to indicate it's mine, and this is the result. This does not quite seem to be the case. I can put a theorem about real normalized differentials and be very sure about it. The answer to these questions 1 and 2 seems to have been emerging independently in thoughts, works of many different people. It seems that at this point in time, at 10:26 a.m. on July 8, I personally believe that we know the correct answer to be, I'll tell you what. At this point in time, I personally will not stake my life on the fact that it's the correct answer and that we have a completely rigorous proof. If somebody in the audience is willing to stake their life, that may be a better argument. I'll look at Matt at the appropriate point and ask about him. But let me first of all mention that this is something that somehow many people have worked on from different perspectives, and this has been happening over a while, and the main part of the preparation for the talk was this table. This is alphabetical. This is sort of chronological. So I'm aware of some notes that I got from Anton of some talk that Kontsevich gave in 2008, where there are some descriptions that has some parts of what eventually will appear on the blackboard. Contat-Gendron, who is here and who is a student of Martin Möller, has a paper on the archive from March. Davei Chen, who is not here, has a paper on the archive from 1504. My student, Haya Norton, has defended her PhD last August, I think, and that's about limits of real normalized differentials. Matt Bainbridge and Davei Chen have been thinking more about this, so from here on it's alphabetical. Because there are no dates, nothing has appeared. So Matt Bainbridge and Davei Chen have been thinking about, I don't know what I wrote here. I was thinking about some completely other things. Pardon. So alphabetic order has been destroyed. But Adrien Sauvager and Dima Zvonkin, as you know, have also been thinking about this. Sorry, Adrien, I don't know what was going in my mind. Gabriel Farkas and Rahul Panharipanda also have been thinking about this. And Igor Krishever, Haya Norton, and myself have been also thinking of this for the real normalized setup, which somehow simplifies some things, makes you suffer for other things, but has very many similarities. And many people in the audience, I know, have thought, and not only in the audience, have thought about this in various guises or shapes, about the limits of differentials. And I'm afraid I might be missing somebody, so I'm very happy to add more names. Anybody wants to have their name added? Anybody wants to have somebody else's name added? Any names I should erase from here? Okay. I'm sorry.
Some aspects. Never mind. It would be.
Anybody else? Yes, of course, Dima Korotkin has described with Zograf, I think, the class of the locus H2 and so on. So this is the preamble to the talk. So now what I'll try to do is I'll do sort of an introduction to some algebraic geometry of curves for you for a while. I'm aware that many of you are familiar with it. I'm also aware of the fact that some of you are probably less familiar, so I hope it will be useful. So my goal at the end is to tell you what I believe to be the correct answer. And when I say I, it seems that we are in agreement with Adrian and Dima. We're in agreement with Matt and Davei. We likely are in agreement with Gabi and Rahul, even though I haven't talked with them as extensively. I agree with my co-authors and so on. So I'll tell you what the correct answer I think is, but I'll be very careful to say what is completely clear and what is not completely clear. So let me try to use the same notation as Adrian. So Hg M1 Mn, this is stratum, and I'm not doing dynamics, and for me meromorphic is going to appear no matter what, so let's start with meromorphic differentials. So this means Mi maybe in Z. Okay? And the sum of Mi is 2G minus 2. Okay? If I have this thing, I can map it to the moduli space of curves of genus G with n marked points. So n marked points. And maybe distinct marked points. And an object in here, you're probably used to drawing this way, something like that, I'm afraid for the purposes of this talk, you must allow me to draw it like this. The reason is that the difficulties appear for rather complicated stable curves. And my drawing skills, of course, will allow me to draw any stable curve this way, but the picture will become much less readable. So this is the picture I draw. So for me, a curve today is a complex curve. So I draw a curve. I put a G because the genus is somewhere in the picture. And then I label the points. Okay? So this is a smooth curve. So this is what an object in here is. And this is the map. Of course, you probably want to projectivize it. And I want to say that for all mi greater than 0, this map phi is injective. Okay? If not, if you have higher order poles, you divide higher order poles, you maybe start worrying. So let me not talk much about that. But somehow I will mentally think, so question, well, I really would like to do the meromorphic case, but let me not do this because I maybe have to decorate this a bit, is I'd like to describe exactly what Adrian was trying to describe. Is equal to what? Okay. Is the font size still okay, Kurt? Or I'll take this as a warning. Okay. Remark number 1. I have to explain to you what this is, right? So M, G, and bar. This is moduli of stable pointed or stable curves with marked points. So let me explain what boundary divisors here look like. So there are loci here that look like this maybe, where you have G minus I on this side, I on this side, and then you have some marked points here and some marked points here. Okay. Let me explain how I'll draw this curve. So the way I'll draw it, it will be this. I'll put a G minus I here, I'll put an I here, and the marked points I'll draw as marked points. Today I'll be drawing these marked points as little crosses because I'll have dots later on when we get to them. Okay? So this is one possibility. So a locus of this sort you can compute the dimension of, so the points distribute whichever way they want. The points, by the way, for me are labeled. I know which one is number 1. That's why I have the 0 of multiplicity M1, of pole, and so on. So this locus, of course, if I think of this locus, this is equal to M G minus I, some N1, plus 1 times M I n minus n1 plus 1. This is what this locus is, because this point here, see this is a dot, where the two components come together, is important. And so on this side I have maybe n1 points, and this is plus 1 point. And on this side I have the remaining points and plus 1 point. So this locus is this. So there is a locus inside this moduli space, which is this. It also contains a locus that looks like this, okay, which I will draw like this. The genus is G minus 1. And so this locus, if you think of it, it's moduli space of curves with genus G minus 1. There is a bunch of marked points here. And there are 2 marked points corresponding to where you have glued this to form a node. So these are examples of stable curves. While we're doing this, let me draw some more pictures of stable curves, and you will see why I really prefer to draw nice pictures. So there is this curve, for example. What does this mean? This means I have 2 components of genera maybe I, and if this is I and I want to be in MGN, the other one better be G minus I minus 1, right? And the marked points live somewhere, okay? So this is a nice picture. If I draw the smooth picture, I can, but it will get slightly bigger. What do you think people call this curve? Well, if you look at this picture, it's clear this is a banana. And this is a standard terminology, really. Okay? I can also draw this curve. So there are 2 components of genera I And if you compute the other genus as G minus I minus 2, you can see the two loops quite clearly. Any guesses what this is curled? Correct. Okay. Let me draw some more. You have this curve. What does this mean? So here I have three curves of general I, J, and the third one, which is this one, is G minus I minus J minus 1. Why minus 1? Again, I have just one loop. So the total, the sum of the genera of the smoothings of the normalizations of the components is G minus 1. So this I would, of course, call a triangle curve. And somehow for the examples I'll eventually do, I'll also have this, which I'll call a square for obvious reasons. Okay. So are these okay? Can you read these pictures now? Okay. So if I want to draw this, in a smooth way, no fun. Okay. So these are examples. So I haven't really defined what MGN bar is. So the conditions are no component of a nodal curve is a P1 with less than 3 points. Okay. And the second condition is that no node is marked, which is to say that I should not allow marked points to be put on top of the node. This is part of the data, right? It's not trivial immediately, at least it's true, it's not hard to prove, that this space will be compact, right? Because I'm somehow disallowing things. So you can imagine I take this curve, and I take this marked point, and I start moving it to the node, right? And this is not allowed. So what's the issue? So let me draw a picture. So suppose I have this picture. Forget the other points, they don't matter. And suppose this curve starts going to the node. What would be the limit? Well, the limit tells you should blow up here. So you insert another component here, which is a P1, and your marked point moved off to here. Okay? So this converges to this. The limit is equal to this. Okay? So this is how you should see that this is a compact space. Notice there is one extra condition I didn't write, which the experts in the audience assumed I forgot to write. The usual condition you write is that no two marked points coincide. Okay? And that would be MGN bar. But actually, for the purpose at hand, for this problem here, you really want the closure of the stratum. In the closure of the stratum, the zeros can easily come together, right? And the zeros can easily come together. You should allow this. There is no reason why you shouldn't. And this can be, okay, you cannot do two at a time, sorry. So there is also a moduli space MGN bar epsilon, where marked points are allowed to coincide. And I will work here. The reason it's called epsilon is somehow the usual space would be 1, which means every point has weight 1, and the total weight of points that come together cannot be larger than 1. If each point has weight epsilon, they can all come together. The fact that you should work on this space, I think, is due to Farkas and Van Haripande. I mean, they were probably the first who officially mentioned it. I don't know. Yeah. But certainly, it's very clear, and they are thinking about this problem. So this means my points are allowed to coincide, which means I will take the honest closure of the stratum and not some partial closure or something like that.
And is this space still compact?
This is still a compact space.
Oh, I see. So points can collide with each
So points can collide with each other. So usually if two points collide, you would need to blow up, you would need to insert a P1, but I just say forget this stuff. So if I have a tree of P1s growing where the points are, I just collapse it. And this is still a good enough space. There is this general Alexeyev, Hassett, many other people program where you can put any weights. And these are all good spaces. Okay, thank you. I think I'm not sure about the attribution. I'm sorry. Certainly, I had nothing to do with it. Adrian? What? The stability conditions are just you erase the third one. Full stop. So any number of points can come together, but they still cannot come to the node. So a node somehow counts with weight 1. The marked points come with weight epsilon. The stuff that comes together can have weight at most 1, which means you cannot hit the nodes with your marked points, but the marked points can come together. Okay? So it's still a nice enough space. I am not going to define this. God forbid. Okay. A complex structure near the boundary. Is given by plumbing deformations. So this is a complex analytic description. If you're an algebraic geometry, you would say some versal deformations. So this means the following. If you look at this locally in some small neighborhood, this is a node. It looks like x, y is 0. And you're going to deform it to this, which is x, y is t. Right? And then t is your plumbing coordinate. So this is to say this is how you go to the boundary. And notice some very important thing, which may be something that flat people need to worry about. So this is a complex space. Forget stack, orbifold, all this nonsense. It's basically, I'm telling you, it's roughly a complex manifold. Okay? And I'm telling you the complex structure. I'm telling you the local complex coordinate near the boundary is that. So if you now want to work with a space using flat geometry, I hope at some point we would be able to establish that the complex structure you get is the same as that. If not, you will have to work hard to prove this is the same complex space, right? Or that it's a nice space. So we have to be careful. Sorry, there will be many technical comments I'll intersperse because this gets tough in various places. Not yet. Okay? So now the question is, what are limits of differentials? What kind of objects are limits of differentials? And I'd like to try to convince you that from the point of view of algebraic geometry, this is clear. This is a priori clear to any algebraic geometer who will think about this. Well, I don't know about any. But this should be rather clear. So what does this mean? So suppose I have a family. This is a family of smooth curves inside MGN. There are also marked points, but I'm omitting them in the notation because it will get too heavy otherwise. And suppose it converges to some nodal stable curve. Okay. Suppose, moreover, I'm sorry, I'll use eta. Is that okay for omega? So eta t is a holomorphic one form on CT. Maybe with prescribed zeros, as we'll see in a second. So let me write with, so that CT eta t lies in my favorite stratum. Okay? Is eta okay? I can write any other letter you prefer except omega. So the reason I cannot write omega will appear in a second, and I don't know any good way to not write that omega, and I'm sure I will get confused. So the question you are asking, let eta 0 obviously be the limit, whatever this means, of eta t. What is it? On C0. Okay? what kind of an object is the limit of holomorphic differentials. So definition. The guy I'll just write is called the relative dualizing sheaf. And I'm sorry, I'll write a correct definition. No, I won't write a correct definition. I'll explain what it is. Relative dualizing sheaf on C node. This is a sheaf. It's not a line bundle. Stalks are rank 1 at smooth points, rank 2 at nodes, and residues must agree. So I can write this more formally, but let me explain in more pedestrian terms what this means. So what I'm saying is if you want to take a section, I will write H naught for the space of sections, okay, of this. An object phi in here is a collection of meromorphic differentials on irreducible components of C node such that at most simple poles at nodes, holomorphic elsewhere, and if I have a node that looks like that, and this is component, so the residue plus the residue is 0. Okay, make sense?
Sir, when you say something is the limit of the sequence of differential, in which sense you want?
I would like to say that this is a natural way to take limits. Okay? So what did I just tell you? I told you there is a space. I'll make a correct claim now. I'm trying to say, to motivate that this is the natural way to do things. You could possibly do other things, but I will do other things in a second, but this is the algebra geometrical is the most straightforward way. So the first claim is that if I compute the dimension of the space, this is G. Which is to say that for any stable curve, I still have the correct number of objects. Okay? And what this means is that so thus rank G vector bundle, which I guess you denote Hg over Mg, extends to a rank G vector bundle Hg bar over Mg bar with fiber over C node being the space of sections. Okay? So this is to say that I can consider over Mg bar global is a family of things which are sections to the relative dualizing sheaves. And this fits together nicely. This is what this says. And so this is the statement I'm making, Dima Korotkin. So I'm saying that this is a rank G vector bundle which naturally extends the total space of the bundle you like. So this is the total space of the Hodge bundle. I would never write Hg, I would write omega Mg. I don't know, but it's your choice. Okay? So this extends naturally. You can ask why this is a natural construction to take. Well, this is a rank G globally defined vector bundle. This is nice enough, right? So if you want to do something radically different, I'm extremely happy to hear about it, but there better be a good reason why that's a good thing. Okay? Yeah. Where? No, so the fiber of a stable curve are these sections. These sections means these are meromorphic differentials on a stable curve that only have simple poles at the nodes, are holomorphic elsewhere, and the residues match up. Huh? At most simple poles at nodes. Was it the font size problem or? Yeah, yeah, Barak?
What is, just in terms of the notation, what is omega C0? What is the
It's a sheaf. It's a sheaf on C0. It's this sheaf which I somehow never defined because I didn't want to write a formula. But I tried to explain that this, I know what it is. I'm told you the space of sections is this things which are meromorphic on each component, simple nodes that match up. Okay? Yeah. You can reformulate this analytically. This is not a definition.
You mean just this? You cannot say it in a shift theoretic.
I can't say it in a shift theoretic way. I mean, this is a push forward of the relative dualizing sheaf or something. I mean, I can do many other things. Yeah, so you can impose such conditions on shifts. It's a rank 2 thing at a node. So at a node, your differential has 2 quote-unquote values on 2 different components, which is why it means rank 2. But then the condition is that the residue is the same. So I don't want to define this, but this I claim as a correct statement. And if you write down the correct definition of this guy, this is what you do. Okay? Sorry, I mean, there will be much more difficult things that we'll have to do. This is a minor cheat. I mean, there is no cheat, it's just correct. Okay? So what's the main difficulty? Difficulty. Because this is really the core of the matter. So you have a family, CT, one parameter, many parameter, let's do one parameter, degenerates into a stable curve. You have a billion differentials, holomorphic one forms degenerating. And you want to know whether a limit point lies in the closure of your favorite stratum HGM1MN. So the difficulty is only one. What if I take A to 0 and restrict it to some V, CV, so this is an irreducible component, some irreducible component of C naught, what if this is identically 0? This is the only difficulty you see. If your limit is nowhere 0, we're done, right? It's very clear. We have this meromorphic guys with matching up residues. If I can find this meromorphic guys with residues matching up such that their zeros have the correct configuration, this is clearly in the limit. This is easy. The problem is, suppose my differential vanishes identically on some component. I have just completely lost all track of the zeros there if I do it naively, right? So this is the only difficulty. This is the difficulty. And how do you do this? How do you deal with this? So I should take my notes because otherwise I'll start telling things. Oh, I thought I had 2 hours. Oh, well. Okay. Let me try to explain the way you should start doing this. So please bear with me with a few 5 minutes of algebraic geometry, then I'll say the same things in a pedestrian way, or I don't know, in a non-algebraic geometry way. And this thing that I'm supposed to do now is called limit linear series. And this is due to Eisenbud and Harris. Okay, they come in white because they have not worked on this problem in particular. And there are hundreds of papers where this is used. This is a well-established technique. Let me try to explain the idea. Okay? Let me maybe go here. So, so let's say d delta is small union disk, which is really somehow sitting inside mg and bar epsilon maybe. And so that 0 sits on the boundary. Okay? So what does this mean? This means I have a family of curves. I'll draw it as a curly C over a disk such that over 0 I have curve C0. This is algebraic geometry notation. Okay? And over this guy, I'll have L. So L is the L restricted to CT is the canonical bundle, the cotangent bundle of CT. L restricted, I'm very good at dropping chalk today. Okay. L restricted to C0 is this relative dualizing sheaf. Okay. So this is this thing you would want to take sections of, right? And so if I think of eta tau, what is this a section of? It's a section of the canonical bundle on CT, of the canonical bundle of CT, and it's supposed to vanish at the collection of prescribed points. So my prescribed points I'll label as pi, and this is, the font is too small obviously, and this is, so this is a section of the canonical vanishing at a bunch of points. Okay? Then eta 0, I describe that by this procedure, it's a section of this twisted by minus the sum of the points. What do I mean by this? This has still nice smooth points on a nodal Riemann surface. They define a line bundle. I can twist by this line bundle. So this means tensor O of this. Okay? And suppose this restricted to some component is identically 0. Then I can just think of eta nod as of eta globally. So this is globally over the family C. This is a global section of the family C of this global thing L, twisted by the sum of mi pi, which are now dependent on t, which is why you don't like heavy notation, and then you further twist it by this component. Let me try to explain what happened. If I have a section of a line bundle, so let me try to explain the general. So if S is a section of a line bundle on a complex manifold variety stack orbifold, never mind, such that for some divisor, which means codimension 1, D inside X, S restricted to D is identically 0, I can think of S as a section of this line bundle twisted by D. Okay? So this basically means the following. Your D is a divisor, maybe irreducible. So it's given by equation f is 0. So if a locus D is the locus where f is 0, this really means S divided by f. Right? If I have f, I define an equation for something where S vanishes, then S over f is globally well defined. And this is what I'm doing here. My eta in this family is a family of differentials which vanishes identically on some irreducible component of the stable curve. So I take out this irreducible component of the stable curve. Look, this is a one-dimensional family. This is two-dimensional. The stable curve is codimension 1. Its irreducible components are also codimension 1. Okay? So this is what you should do. So this is, and if you do this, this is limit linear series. You have to work much harder. So after suitable twists, we'll get the limit of eta to be non-identically 0 on any component of C0. And then we would be very happy because we would have non-zero objects, and that's exactly our goal. Because if we have a non-identically 0 object, we can look at its zeros. There is one problem. No general theory of limit linear series exists. So you can't do this in general. The issue is basically that you can start twisting on one component, then twisting on the other, and then you keep twisting and twisting and twisting, and where on earth do you know when to stop? So what does this procedure correspond to? It means I somehow rescale in the family. So if my eta 0 was like t to the k, I mean near 0, times something else, I basically take out the vanishing order. But you need to do this in a smart way. So there is no general theory of limit linear series exists, but this is okay for the following list of situations. Irreducible stable curves. Irreducible stable curve means a curve that looks like this. It only has one irreducible component. The reason it's okay here, I don't even have to do anything. I have a differential which does not vanish identical in the whole thing. If it vanishes identical, I take out the 0, no problem. Okay? It works fine for curves of compact type. Which are things that look like that. Okay? So this means there is somehow no loop in the graph. In the dual graph, but never mind the word dual graph. There is somehow no loop. You cannot go around through one node and come back to the same component. Why is it okay here? Because here I know when to start. Let's look at that component. Let's make sure things are non-zero there. Done. Rescale it, throw it out. Continue. There is somehow a well-defined inductive procedure. Oh, this guy could be a tree. Sorry, this is not a tree-like enough object. This looks better? Huh? These things. Okay? I have not drawn any dual graphs, and I will desist because I don't have enough time. Okay. Yeah, so this, you see, if I do that, this thing could still vanish on D if it vanishes to high order. So the issue is I'll need to put K here, and then the game becomes very complicated as to how many Ks I put where. Carlos, I'm supposed to stop at 11:15 or 20 or 1? Okay. Okay, so I'm continuing from that blackboard over there. Works for curves of pseudo-compact type. This is an observation of Dewey Chen, to the best of my knowledge. So these are things that basically look like compact type, but each of the things is irreducible. So you draw this, then you draw this, and then maybe from here grows another one, and grows another one, but something like that. Again, the same thing works. On each irreducible curve, no issue. You start from a side, you keep going. So there is an extremely complicated, there is a very complicated theory for curves with two components. So this includes the banana and the dollar. And this is due to Esteves and Medeiros. And this is a, I forget, 60-page, 70-page paper in Invenciones, and it's very hard. I cannot state you the answer in a reasonable way on the blackboard. Not in general. Okay? And there is a good reason it doesn't work in general, it just the procedure doesn't stop. Okay, so let me, for a banana already, the simplest procedure does not stop. So let me try to rephrase what this procedure does in pedestrian terms, and then it will be maybe clearer. In pedestrian terms, simpler terms, of course I'm losing something. Maybe I should write in biking terms. This is not quite pedestrian. In simpler terms, in a family parametrized by t, we rescale components by different powers of t. We rescale eta on various components by different powers of t. So it means at nodes it may acquire higher poles, for example. And zeros. Okay? So the example of the difficulty would be the following. So here is my banana curve. So on this side here, I need to somehow rescale and twist. So maybe if I rescale and twist, I end up with a pole of the order z to the minus k here, and a 0 of the order z to the k here. And then on the other side, you can compute that what you would be having, I don't know, z to the l, sorry, but maybe z to the k plus 10. Maybe this is your situation. Then on the other side, you can see that you will have a pole of the order this, and 0 of the order this. And then you never know where to stop. You can keep increasing the pole order here and the 0 order here. Such things may exist for very high k, and I don't know where to stop. This picture is hard for you to imagine because you're probably thinking of the flat picture. So the flat picture says, if I look at the set of components, the big ones where the form is big, the smaller ones, the still smaller ones, and so on. And this is precisely true. And this is why in this situation, from the flat point of view, even though the general theory of limit linear series for any line bundles doesn't work, here it works. Okay? So let me try to tell you what form the answer should have. Form of the answer for describing whether C node lies in the closure of your favorite stratum. The C node question? Okay. So you take a point in here, maybe with an epsilon, and you want to know whether such a thing lies in here. So what does this limit linear series business tell you? What I said so far is somehow rather clear mentally. It does not prove that the form of the answer right now actually is possible, but this is the form of the answer you would expect. So you would expect theorem, which looks as follows. C node P1 Pn lies in the closure of a stratum if and only if for any irreducible component CV of C node, there exists a a differential omega, eta, not omega, eta v, which is a meromorphic differential on CV with some poles at some nodes of C node contained in CV. I'll need to continue on the next blackboard, sorry. such that if a marked point Pi lies in CV, then the order of eta V at Pi is equal to Mi, and the set of eta V satisfies some conditions. Okay? So all I said was the following, that if you take a stable curve, so you take a nodal curve with a bunch of marked points, and you want to know whether it lies in the closure of the stratum, what you're supposed to check is the following. You're supposed to check that on each component there exists some differential, which by this procedure should be polar. It should have some higher order pole at some nodes. And you should have this collection of differentials satisfying some conditions. Of course, I have cheated completely. And that would be your answer. So the question is, what are these conditions? But you know, sort of, that this is a...
What's MI in this statement?
MI as a multiplicity. So we're talking about HG M1 through Mn. So this means for me, eta T is a section on CT of the canonical bundle twisted by minus sum of MI Pi. Okay? So basically, take an irreducible component of the stable curve. You certainly want there to be a meromorphic differential on that component, which has poles at some of the nodes with some order, and such that it vanishes at the zeros that are ending up on this component. And then there should be some conditions. Okay? So that's the form of the answer should take. And if you want to ignore all of my discussion about limit linear series, this is just my motivation, explanation, not quite proof, but basically a proof, that this is the form the answer should take. Okay? So the question is, what are these conditions? So condition. Huh? Yeah. They might coincide, then you just add them up together, you don't worry. I mean, if 2 points P are the same, you twist by, so if points come together, the zero multiplicity just adds up. That's not the difficulty. At least that's not a difficulty I'm aware of. Yeah. So why do I write eta V? So I'm mentally thinking of the dual graph. I need to label components somehow. I label them by vertices of dual graph. If you have a better suggestion, that's fine. But okay. So I need to write what conditions they satisfy. And let me try to explain that a couple of conditions are very easy to understand. So conditions, when I start writing conditions, there was Contant Gendron. I wrote down the first two conditions I'll write down, and Dawei Chen further elaborate on some of them, and I'll try to phrase the answer in a different term. So what I'll do now is I'll write two easy conditions, and then since I'm running out of time, I'll try to state a general answer, and I'll promise there is something about real normalized differentials that I won't tell you about. And then if we have time, I'll take a question from the audience in the form of a graph of a curve, and I'll tell you how this works. Okay? One is the following condition. If I have two components, CV and CW, that meet at a node, okay, then if eta V is holomorphic at P, then I need to have a condition that the order at P of eta V plus the order at Q of eta W is at least minus 2. Okay? Why is this an obvious, sorry, not obvious, why is this as clear as these conditions should be satisfied? We started with things that are allowed to have simple poles. So I'm allowed to have simple poles on both sides, and then I twisted one component, which means I reduced the order of pole on one side, and I paid for that by increasing the order of pole on the other side, and this balanced out. So it should be minus 2, well, it could be less. You know, if I'm allowed to have a higher order pole, it may happen to be lower. And I can have arbitrary residue for A to W. I mean, arbitrary is actually a wrong statement, but there is no local condition for the residue. If I have a higher order pole, it might have a residue. Second, if in the same situation, if I have a node and both of these guys have simple zeros, then the residues match up. That's what you expect. This means you did not twist this node, or you twisted both components the same way. So you are still ending up with two simple poles, and then the residues must match up. So these two conditions are written down by Contat-Gendron, and I tried to explain why you would expect them to be true. This actually proves that they're sufficient if you do it carefully, and Contat certainly does that. Okay? And then there are examples that show more conditions are needed. Okay? More conditions. Mm-hmm.
Okay, so if it's not holomorphic, if they're both poles, they have to be.
They can, yeah. So the only possibility for them to both be polar if they are both simple poles.
And then they have to be orthopoles.
And that, sorry, simple poles with same residues. Okay. So so let me explain why more conditions are. It is impossible to have. I'd like to explain why these are not sufficient conditions. It's impossible to have the following situation. It's impossible to have two components, that meet in 2 points, such that on this component here I have, z dz, which means on the other component I have z to the minus third dz, and here suddenly they have simple poles. This is impossible. This should be disallowed because when I'm twisting by an entire component. And if I have simple poles here, this means I should have twisted both components the same way. So this should not happen. Similarly, it should not happen that here this component sort of dominates as regular, and here this component dominates as regular. This should also be impossible. So that's an easy condition to impose. It just requires a different viewpoint, which is less local. And then there is a residue condition, which is more difficult to state. Okay, so let me try to write the conditions. So now comes the most difficult part of the talk is what word I write now. So I could write a guess. I could write a theorem. I could write possible answer. I don't know. So this depends on what level of certainty I'm exhibiting and the answer I will give to you. And let me say that certainly there are people here who have contributed to understanding this and who may understand this completely, including that this is a theorem without a question mark, I don't know. So Bainbridge Chen, Sauvager Zvonkin. Farkas Panhariponda. Yeah, it's not clear who will the authors of a potential paper be. It could be a union of these people, subsets, intersections, I don't know. The intersection would be empty, which would mean we're in trouble. Okay, my name may, well, I don't know. I also have some thoughts. So let me try to say what the conditions are. So first, have a partial order on components, on irreducible components of the dual graph, of C0, which says if CV intersects CW is non-zero, then we have either, well, we can compare them. Okay, but this is all the comparison we have. I don't know by how much they differ. and the comparisons have to be transitive. And it says the following: if CV and CW meet at a node Q, then they're equal, means that the orders of both differentials are 1. Well, maybe there is no pole, so I have to write at least -1. CV is greater than CW, means the order of at P of A this is at least 0. It means just on this side the differential is regular. On that side the order is controlled by that condition. So what I just wrote down completely takes care of that. Okay? And because I have an ordering on two components, I know which one dominates. So this was the easy part. Now comes the hard part, and 2 minutes, okay? Okay, residue condition. I'll write a technical statement which I hope is correct, and then I'll stop, and if you have questions, we'll have to discuss elsewhere. So take the full set, the set of all minima of the set of components. This is a partial order. It doesn't have a unique minimum, but it might have a bunch. Okay? Let their union be C node null inside C node. Let C node non-null be the rest. Okay? Then the residue condition is to say that for any connected component C prime of C null non-null the sum of the residues at the points where C node null intersects this thing is 0. The sum of the residues on the null part. Okay? And then you apply this inductively. Okay? So I was hoping to do some examples of this by popular demand, but for the purposes of having lunch, this seems impossible. So I'll stop, and I'm happy to explain how this works in any detail. Thank you.